On October 3rd, 2025, something unprecedented will happen. An interstellar visitor designated 3I/Atlas will sweep so dangerously close to Mars that every operational spacecraft and rover will face humanity's first true off-world disaster scenario, while Earth watches helplessly from behind the sun's blinding glare. What scientists initially dismissed as a routine flyby has transformed into something far more sinister. A comet pulsating with carbon dioxide, erupting with inexplicable brightness surges, and defying every fundamental principle of solar system dynamics. The official forecast remains suspiciously silent about the communication blackout, the erratic energy pulses, or the catastrophic possibilities if Mars' orbital fleet suddenly loses contact with Earth. The question looming over mission control isn't just what 3I/Atlas will do to Mars. It's what horrors might unfold during those critical hours when no one on Earth can see what's happening. October 3rd, 2025 represents more than just another milestone on humanity's exploration timeline. For the first time in recorded history, an object born in another star system will tear through the Martian vicinity, while an entire armada of orbiters and surface rovers operates at full capacity. There's no playbook for the scenario, no historical data to consult, no test runs. Every probe orbiting the red planet, every robotic explorer traversing its rust-colored surface, has suddenly become an unwitting participant in a live-fire experiment in planetary defense. The raw numbers are staggering enough to make any mission planner's blood run cold. 3I/Atlas will hurtle past Mars at a distance of approximately 30 million kilometers, roughly 75 times the Earth-Moon separation. To the untrained ear, that might sound like a comfortable margin of safety, but in astronomical terms, it's practically a knife-edge pass, especially when you're dealing with an interloper rocketing through space at nearly 68 kilometers per second. Mars has never encountered an interstellar visitor at such close quarters, much less while hosting billions of dollars worth of irreplaceable scientific hardware. What amplifies the stakes exponentially is the timing of the blackout. As 3I/Atlas makes its closest approach, Mars will disappear behind the sun from Earth's vantage point, creating a communication dead zone lasting more than a month. Ground controllers will be flying completely blind, powerless to intervene if disaster strikes. The risks aren't abstract thought experiments. They're measured in billions of dollars of investment, decades of accumulated scientific knowledge, and the survival of humanity's first functional planetary network beyond Earth. October 3rd is a day when the theoretical danger of interstellar objects crystallizes into an inescapable, irreversible reality check. 3I/Atlas, officially recognized as the third confirmed interstellar object to penetrate our solar system, refuses to behave like anything in the celestial rulebook. At first examination, it resembles a typical dirty snowball on a hyperbolic escape trajectory, screaming past Mars at nearly 68 kilometers per second, fast enough to traverse the entire continental United States in less than 60 seconds. But the deeper scientists probe, the more disturbing 3I/Atlas becomes. Its point of closest approach, between 0.19 and 0.20 astronomical units, translating to roughly 30 million kilometers from Mars, places it squarely within what planetary scientists consider the danger zone. It's close enough for Mars-orbiting spacecraft to capture crucial details that Earth-based telescopes could never resolve, yet near enough to pose genuine threats. What truly unsettles researchers isn't merely the velocity or trajectory, it's the bizarre chemistry. 3I/Atlas sports a coma overwhelmingly dominated by carbon dioxide, not the water vapor that characterizes typical comets. In most cometary visitors, water ice forms the primary volatile component. But here, carbon dioxide outgassing drowns out everything else. The ratio is so extreme that it's forcing astrophysicists to fundamentally reconsider what interstellar chemistry can produce. Then there are the brightness outbursts, violent, erratic surges that spike and collapse without warning or pattern. The plume geometry defies computational models. Jets erupt at inexplicable angles, and the entire gaseous envelope appears to pulse with energy, as though something trapped inside is violently struggling to break free. For planetary scientists, 3I/Atlas represents less of a predictable visitor and more of a cosmic wild card. Its chaotic behavior, its alien chemical signature, and its tremendous velocity all converge on the same unsettling question. What else is concealed within this object? And how will Mars react when it passes directly through the crosshairs? From October 1st to November 9th, 2025, both Mars and 3I/Atlas will vanish into an observational blind spot, positioned less than 30 degrees from the Sun as viewed from Earth. For mission controllers, this translates to more than a month of enforced radio silence, with every communication signal forced to pass through the Sun's overwhelming electromagnetic interference. No ground-based telescope, no deep space antenna array, not even the technological marvels of the James Webb Space Telescope or Hubble can track the comet during its closest approach. The only functioning eyes will belong to the orbiters circling Mars itself. MAVEN, the Mars Reconnaissance Orbiter, the Trace Gas Orbiter, Mars Express, and Tianwen-1. These spacecraft will become the sole witnesses to whatever unfolds, relaying fragmented data packets across a communications chasm capable of swallowing anything from a minor outburst to a civilization-ending catastrophe. The blackout isn't merely an inconvenience. It's a critical vulnerability in our planetary defense architecture. If 3I/Atlas fragments undergoes a catastrophic brightness increase, or exhibits behavior never before witnessed, Earth won't receive the information in real time. Engineers have rehearsed contingency protocols for years, running simulation after simulation. But as a conjunction window opens, every carefully planned scenario becomes a gamble with cosmic dice. In control rooms across the globe, teams steel themselves to the possibility that the most significant discoveries or disasters will occur completely unobserved, with only the faintest electronic whispers making it through the static to hint at what transpired in the darkness. Imagine a city-sized object from another star system hurtling past Mars at interplanetary velocity, and then suddenly disintegrating. That's the scenario haunting analysts at the European Space Agency and NASA's Jet Propulsion Laboratory during sleepless nights. When a comet like 3I/Atlas fragments in proximity to a planet, it doesn't simply disappear. Instead, it seeds the entire orbital neighborhood with a swarming debris field that can persist for years, even decades. Each fragment, ranging from boulder-sized chunks to vast clouds of microscopic dust, follows its own independent trajectory. Some graze the upper Martian atmosphere, generating spectacular meteor displays. Others loop into temporary gravitational capture around the planet, creating unstable orbits that could last months or years. The result isn't a single discrete event, but rather the spontaneous creation of a shifting, lethal minefield. Computational models demonstrate that even a moderate breakup event could scatter thousands of fragments, ranging from meter-scale shrapnel to massive blocks hundreds of meters across. Some of these get gravitationally snagged by Mars, circling the planet in chaotic, unstable orbits before either spiraling down to the atmosphere or slingshotting away into interplanetary space. Others drift into crossing trajectories with Phobos and Deimos, Mars' fragile, potato-shaped moons, or linger in precise orbital corridors currently used by spacecraft. Each subsequent pass through these debris lanes increases the probability of collision, not just immediately, but for every future mission attempting to thread through this cosmic gauntlet. The risk doesn't expire after a single Martian season. Debris clouds evolve over time, fragment further through collisions and thermal stress, and spawn new hazards with every passing Martian year. The ESA's Near-Earth Object Coordination Center warns that the worst-case scenario isn't necessarily a dramatic, Hollywood-style impact. Instead, it's a slow-motion cascade, a Kessler syndrome-like belt of debris that could eventually transform Mars' orbit from a gateway to exploration into a spacecraft graveyard. For Mars, and for every robot or future astronaut attempting to reach it, the legacy of a fragmented interstellar visitor might not be measured in crater dimensions, but an invisible, persistent thread of lethal shrapnel drifting through the crimson Martian skies for generations to come. A city block-sized fragment from 3I/Atlas striking Mars at 68 kilometers per second would unleash more kinetic energy than humanity's entire nuclear arsenal detonated simultaneously. The numbers transcend human comprehension. A 1-kilometer nucleus traveling at that velocity carries sufficient kinetic punch to excavate a crater up to 35 kilometers in diameter, an impact scar that will remain visible from orbit for millions of years. The initial shock wave would instantaneously vaporize rock, flash fry the surface to temperatures exceeding those in a star's corona, and hurl billions of tons of pulverized dust into Mars' thin atmosphere. For the robotic explorers on the ground, Perseverance, Curiosity, Zhurong, there would be no shelter, no escape protocol. Dust would descend in a suffocating curtain, blanketing solar panels in an opaque shroud, clogging delicate filters, and plunging the entire planet into an artificial twilight. Even nuclear-powered rovers would struggle to maintain operations as the sky dims to perpetual dusk and surface temperatures plummet. But the devastation wouldn't be confined to ground zero. The Titanic explosion would inject fine dust particles and aerosols high into the Martian atmosphere, scattering and absorbing incoming sunlight while triggering a planet-wide dimming effect. For months, potentially years, Mars could experience a form of artificial winter, temperatures dropping precipitously, sunlight reduced by half or more, and an entire surface shrouded beneath a copper-colored haze of suspended particles. Orbiters flying overhead would confront their own existential crisis. The electromagnetic pulse generated by the impact, amplified by swirling clouds of electrostatically charged dust, could scramble sensitive sensors, trip automated safety systems, and knock out communication relays. Engineers on Earth, already rendered blind by the solar conjunction, might not discover for days or even weeks whether their spacecraft survived the initial blast. In mission control rooms around the world, every lost signal would feel like a physical blow, a stark reminder that Mars has suddenly become a testing ground for the unthinkable. What happens in the aftermath depends entirely on what remains functional after the dust literally and figuratively settles. Invisible threats don't leave dramatic scars on planetary surfaces, but they possess the power to scramble a world's entire electromagnetic nervous system. As 3I/Atlas sweeps past Mars, it drags an enormous cloud of ionized gas and dust, plasma threaded with energy, straight through the Martian neighborhood. Unlike Earth, Mars lacks a global magnetic field for protection. Its tenuous atmosphere and patchwork of localized crustal magnetic fields make it particularly vulnerable to electromagnetic disturbances. Scientists who specialize in space weather know exactly what happens when a comet's plasma tail brushes against a planet. In 2014, comet sighting spring-triggered auroras across Mars, brief, ghostly curtains of ultraviolet light far more intense than anything previously observed. But 3I/Atlas represents an entirely different beast. Its coma is extraordinarily rich in carbon dioxide, primed to pump out charged particles at rates Mars orbiters have never measured before. During the flyby, the entire ionosphere could surge dramatically, illuminating the sky with planet-wide auroras, while flooding the upper atmosphere with high-energy electrons. This isn't merely a spectacular light show for future tourists. Surges in ionospheric density can overload spacecraft sensors, trigger fault protection systems that shut down critical instruments, and potentially knock out communication relays entirely. The magnetic anomalies concentrated in Mars' southern highlands act like natural amplifiers, focusing electrical currents and spawning localized storms of electric charge. Engineers particularly worry about single-event upsets, microscopic, invisible jolts of radiation that can flip individual memory bits, scramble navigation systems, or force an orbiter into protective safe mode without any warning. Even without a single physical fragment striking Mars, the electromagnetic aftershocks from 3I/Atlas could ripple through every operational system in orbit. For mission controllers, the genuine hazard may prove to be the threat that leaves no visible crater but renders the entire Martian fleet temporarily blind, deaf, and unable to respond. Planetary protection officers have invested years preparing protocols for biological ambiguity, but nothing in their extensive handbook covers an interstellar object potentially laced with alien organic compounds. As 3I/Atlas sweeps past Mars, its CO2-rich coma isn't merely a chemical anomaly. It's potentially a delivery mechanism for complex carbon compounds, possibly even pseudo-biological molecules that blur the line between chemistry and life. If fragments or dust particles from the comet intersect Mars' atmosphere or settle onto the surface, every future biosignature experiment will face a profound new dilemma. How do you distinguish authentic Martian life from interstellar contamination? Even a handful of organic-rich grains could irrevocably blur the distinction between native Martian chemistry and imported cosmic noise, transforming humanity's search for life into an endless debate over false positives and ambiguous results. But the potential fallout extends far beyond test tubes and mass spectrometers. If larger fragments cross paths with Phobos, Mars' innermost moon, the consequences could play out on a planetary scale. Phobos is already structurally compromised, riddled with deep fractures throughout its interior. Its internal structure barely maintains coherence under the relentless tidal forces exerted by Mars. A severe sandblasting from cometary debris could accelerate its ongoing breakup, scattering rubble into orbit and potentially forming a temporary ring system around Mars. For orbiters and all future missions, that wouldn't merely represent a navigation hazard. It would create a moving minefield populated with fragments large enough to obliterate satellites or trigger cascading collision events. In an absolute worst-case scenario, Mars could gain a ring system overnight, while simultaneously losing safe access to its orbital space for years or even decades. Not every fragment ejected from 3I/Atlas will remain confined to Mars' orbital neighborhood. Some pieces, nudged by the subtle but relentless pressure of sunlight, a phenomenon known as the Yarkovsky effect, will begin a slow gravitational drift. Their orbits will stretch and shift over decades, following pathways that computational models struggle to predict with certainty. For planetary defense strategists, this represents the nightmare in extreme slow motion. Debris that escapes immediate detection can quietly migrate to the inner solar system, sometimes eventually crossing Earth's own orbital path. Gravitational resonances with Mars or Jupiter can amplify this drift, pumping fragments onto entirely new trajectories that intersect with future spacecraft lanes or, in rare but non-zero probability cases, Earth itself. Most fragments will never approach our planet, but even a 1 in 1,000 chance accumulating over a century is sufficient to keep risk assessment analysts perpetually on edge. These rogue fragments don't advertise their presence. Their irregular thermal properties, asymmetric shapes, and unpredictable rotation rates make them significantly harder to detect and track than conventional asteroids. Detection systems specifically engineered to identify typical near-Earth threats might completely miss a city block-sized relic from another star system tumbling through orbital planes that no one thought to monitor. The ultimate legacy of 3I/Atlas, then, extends far beyond localized chaos around Mars. It's a long tail of uncertainty stretching across decades and potentially centuries, with Earth as an unlikely but not impossible endpoint. Every fragment that escapes becomes a question mark hanging over future generations. Mars exists as a planet defined by its precarious balance, a thin atmosphere barely capable of retaining heat, rusty dust covering ancient geological mysteries, and just enough sunlight reaching the surface to prevent the entire world from freezing solid. When an interstellar object, like 3I/Atlas, sweeps past, trailing a coma rich in carbon dioxide and dark, light-absorbing dust, even a near miss can fundamentally tip the scales. A sudden injection of carbon dioxide and fine particulate matter doesn't merely cloud the Martian sky. It fundamentally alters how much solar radiation reaches the ground, shifting the planet's albedo, its reflectivity, by fractions that carry enormous implications for climate models and surface mission operations. A darker Mars absorbs more heat, while paradoxically, suspended dust can simultaneously cool the surface by blocking incoming sunlight. Extra atmospheric carbon dioxide could complicate everything from rover power generation budgets to ambitious future plans for in-situ resource utilization. But the physical and climatological fallout isn't the only ripple effect. With the planet concealed behind the sun, unverifiable rumors inevitably outpace verified data. Social media platforms fill the information vacuum with wild speculation, accidental terraforming through cosmic disaster, secret impacts covered up by space agencies, even conspiracy theories about deliberately redirected comets. Mission planners and planetary protection officers find themselves fighting not just against physical dust, but against a spreading cloud of viral misinformation. The genuine hazard, in the end, may not be the physical effects of the comet's passage, but rather the narratives that proliferate in the darkness, stories that reshape public trust and alter the trajectory of Mars exploration long after the last dust particle has settled back to the surface. Late October 2025 represents a catastrophic convergence of cosmic forces. 3I/Atlas reaches its perihelion, closest approach to the Sun, at 1.36 astronomical units precisely as solar cycle 25 crests toward its maximum intensity. Space weather forecasters brace for a dramatic spike in solar activity, coronal mass ejections, solar energetic particle storms, and shock waves capable of rattling the entire inner solar system. During solar maximum, the sun unleashes 4 to 6 major eruptions every single week, with solar wind velocities surging past 1,000 kilometers per second. Now inject into this already volatile environment a carbon dioxide-rich interstellar comet sporting a sprawling plasma tail, and the risks multiply exponentially. If a massive solar storm slams directly into 3I/Atlas's coma while Mars sits in the crossfire, the resulting electromagnetic turbulence could dwarf anything observed during the last major Martian comet encounter. For the fleet of orbiters and surface landers, this represents a perfect storm in its most literal sense. Stacked hazards, unpredictable plasma flows, and a communication blackout window, when every early warning system is already straining to maintain basic functionality. It's not a question of whether systems will be stressed. It's a question of which systems will fail first, and whether redundancy protocols will hold. Asset attrition models paint a chilling portrait of potential losses. If 3I/Atlas fragments catastrophically, or one of its city block scale core pieces strikes Mars, the consequences will unfold in slow motion, but with relentless, inexorable certainty. Dust clouds injected high into the thin Martian atmosphere would slash incoming sunlight by half or more, dropping surface temperatures by as much as 20 degrees Celsius for months or potentially years. Solar-powered rovers would grind to a permanent halt beneath a thick copper-colored haze, their panels unable to generate sufficient power for even minimal operations. Orbiters would lose star tracker lock, their primary means of determining orientation, then gradually vanish from telemetry as successive electromagnetic pulses sweep through the ionosphere, frying circuits and corrupting data storage. Within weeks of the initial event, mission control rooms would receive nothing but silence from half the fleet. The loss wouldn't be measured merely in hardware replacement costs. It would represent the permanent erasure of decades of accumulated Martian climate data, irreplaceable biosignature experiments, and the destruction of humanity's only functional observational network on the Red Planet. For mission risk assessment officers, the absolute worst-case scenario isn't a single dramatic impact with immediate, obvious consequences. It's a drawn-out artificial winter, a planet-wide communications blackout, and the permanent destruction of a generation's worth of work in planetary exploration. It's watching helplessly as years of investment and discovery slowly fade to black. Preparedness in this new age of interstellar risk requires more than merely watching the skies with better telescopes. It demands an entirely new architecture of planetary defense, one capable of functioning autonomously even during complete Earth communication blackouts. In the aftermath of the 3I/Atlas encounter, space agencies and independent observatories worldwide are calling for a dedicated early warning network that spans not just Earth, but Mars, its moons, and the vulnerable corridors between worlds. The lesson emerging from this close call is brutally clear. Every gap in sensor coverage represents a critical vulnerability. Every delay in data transmission can transform legitimate uncertainty into panic and wild speculation. Real-time signal analysis, continuously tracking electromagnetic surges, spectral shifts in comet composition, and atmospheric dust opacity must become the fundamental backbone of readiness protocols. The push for open, transparent data sharing grows stronger, with scientists across disciplines arguing that radical transparency represents the most effective antidote to rumor and misinformation. In the shadow of the unknown, the next infrastructure priority isn't merely to detect another 3I/Atlas. It's to construct a comprehensive monitoring system capable of spotting the subtle anomalies, the silent threats, and the strange outliers before they rewrite the operational rules for every world humanity hopes to explore. On October 3rd, 2025, 3I/Atlas will pass within 0.19 to 0.20 astronomical units of Mars, approximately 30 million kilometers. This encounter marks the first time a confirmed interstellar object has approached so closely to a planet hosting active robotic missions, fundamentally highlighting the unique planetary defense challenges of the interplanetary age. Accumulated evidence demonstrates that 3I/Atlas behaves unlike any typical comet in our solar system. Its carbon dioxide-dominated coma, wildly unpredictable brightness variations, and anomalous plume geometry systematically challenge every existing computational model. The weeks-long solar conjunction blackout means that critical observational data will be significantly delayed or entirely missing, leaving mission controllers almost entirely dependent on Mars-based sensor platforms operating autonomously. Official impact risk assessments thoroughly document potential threats from catastrophic fragmentation, severe electromagnetic disturbances, and persistent long-term debris hazards. Yet the true extent of atmospheric disruption or orbital space contamination remains fundamentally unknown until after fact. What has become undeniably clear: planetary defense teams and space science organizations are already implementing major updates to monitoring networks and emergency response protocols. The 3I/Atlas flyby, regardless of ultimate outcome, marks an irreversible turning point in human space exploration. It forces humanity's nascent solar system civilization to directly confront hazards originating from beyond our cosmic neighborhood, threats we're only beginning to understand how to detect, track, and potentially mitigate. The age of interstellar planetary defense has arrived, whether we're ready for it or not. At 14:37 Universal Time Coordinated on October 3rd, 2025, the Mars Reconnaissance Orbiter detected something that made every alarm in its autonomous threat assessment system scream to life. The automated message, transmitted with maximum priority encryption, took 22 minutes to crawl across the void to Earth's deep space network. By the time it arrived, decoded, and routed to JPL's Mars Operations Center, 3I/Atlas had already begun its transformation. Mission controller Sarah Chun was the first to see the data stream. Her coffee cup froze halfway to her lips as the numbers scrolled across her display. The comet's brightness had spiked by a factor of 40 in less than 6 minutes. Not the gradual outburst modeled in simulations. This was explosive, violent, and accelerating. "We're seeing fragmentation," she announced, her voice cutting through control room's control chaos. Multiple debris streams. Maven confirms plasma density off the charts. We're in uncharted territory. But they were witnessing history through a pinhole. Mars Saturday, April, 28 degrees from the sun, squarely in the blackout zone. Every telescope on Earth was blind. The only witnesses were machines orbiting Mars itself, and their testimony arrived in agonizing fragments, each message taking over 20 minutes to reach human eyes. Hour 1. The trace gas orbiter captured thermal imaging that revealed the terrible truth. 3I/Atlas hadn't just fragmented. It had shattered into at least 17 major pieces, each trailing its own debris field. The largest fragment, designated Atlas Prime, measured nearly 2 kilometers across and was tumbling directly toward Mars' orbital corridor. Hour 3. Tianwen-1's radar detected something nobody had predicted. The fragments weren't dispersing randomly. Mars' gravity was already bending their trajectories, pulling them into temporary capture orbits. The planet was about to gain dozens of deadly new moons, each following chaotic, unpredictable paths. Hour 5. The electromagnetic storm hit. Maven's magnetometer readings went supernova as 3I/Atlas's plasma tail, supercharged by a perfectly timed coronal mass ejection from the sun, slammed into Mars' ionosphere. Across the planet, auroras erupted in a continuous sheet of green and violet light, visible even in daylight, a spectacle no human eyes could witness. Hour 7. The first casualty. Mars Express, the European Space Agency's oldest orbiter, stopped transmitting mid-sentence. Engineers on Earth debated frantically, had it been hit by debris or had the electromagnetic pulse forced into safe mode. They wouldn't know for weeks. On the surface, Perseverance watched the sky transform. Its navigation cameras, designed for terrain mapping, captured something unprecedented. The Martian skies slowly darkening as a vast dust plume from the fragmenting comet began to spread across the upper atmosphere. The rover's AI, Program for Geological Research, made an autonomous decision that would later be called either brilliant or reckless. It began a full-spectrum analysis of the descending dust. Dr. Michael Foster, Perseverance's lead scientist, watched the data arrive with growing horror and excitement. The composition was impossible, complex organic molecules with isotope ratios that didn't match anything in the solar system. carbon chains that looked almost biological, but with a hand deadness that suggested they'd formed in an entirely different stellar environment. It's contaminating every square meter of the landing site, Foster muttered, running his hands through his hair. Every future biosignature study just became a nightmare. But my God, we're analyzing matter from another star system. The rover continued its work as the sky overhead grew darker. Its nuclear power source meant it would survive what was coming. But the solar-powered Ingenuity helicopter, perched nearby, had just flown its last flight. At hour 14, the Mars Reconnaissance Orbiter transmitted an image that would become iconic in the history of planetary defense. Atlas Prime, the largest fragment, captured in terrifying detail against the rust-colored face of Mars. Impact probability calculations scrolled across displays in control rooms worldwide. 67% chance of atmospheric entry within 96 hours. The fragment would miss direct surface impact, barely. Instead, it would perform what scientists called an atmospheric skip, grazing the upper atmosphere at hypersonic velocity before careening back into space. But that graze would be catastrophic enough. The shock heating would vaporize hundreds of tons of cometary material directly into the Martian atmosphere, injecting it with exotic chemistry, while generating an electromagnetic pulse that could fry every unshielded circuit in orbit. In the JPL Operations Center, Director James Harrison faced an impossible choice. Mars orbital assets represented $14 billion in hardware and 20 years of cumulative scientific data. He could order them to fire their thrusters, boosting to higher orbits to escape the worst of the electromagnetic storm. But each maneuver consumed precious fuel needed to keep those satellites operational for years to come. If we boost and nothing happens, we've killed the extended missions, argued one engineer. Some of these birds will have to deorbit years early. If we don't boost and the pulse hits, we lose everything, countered another. Harrison made his decision with 30 seconds of deliberation. Boost them all. I'd rather explain early mission endings than permanent mission endings. Execute the burn sequence. At hour 21, Atlas Prime kissed Mars' upper atmosphere, an altitude of 89 kilometers, traveling at 67.8 kilometers per second. For exactly 43 seconds, the fragment became a meteor brighter than both Phobos and Deimos combined, a blazing sword cutting across the Martian sky. The shock wave it generated was visible from orbit as a rippling disturbance in the atmosphere, expanding outward from the entry point like a stone dropped in a pond. Temperatures at the boundary layer spiked to over 11,000 degrees Celsius, hot enough to vaporize carbon dioxide ice and decompose the exotic organic molecules carried by the comet. The electromagnetic pulse arrived like a hammer blow. The Mars Reconnaissance Orbiter, despite boosting to a higher orbit, saw 3 of its 7 instruments momentarily glitch. The Trace Gas Orbiter lost star tracker lock for 16 terrifying minutes. Tianwen, one automatically cycled through its backup systems, each one struggling to maintain coherence in electromagnetic chaos. On the surface, Perseverance recorded the shockwave's passage as a brief pressure spike, barely detectable in the thin Martian air, but unmistakable in the data. Then came the dust, not the fine, flour-like dust of Martian storms, but something darker, grittier, laced with carbon compounds that had never before touched the red planet's surface. The rover's cameras captured the moment the artificial twilight began. Within hours, the sky dimmed by 30%. Within days, it would be 50%. Mars was entering an artificial winter, and nobody on Earth could do anything but watch the delayed data streams and wait. But in that darkness, something extraordinary happened. Curiosity, operating alone in Gale Crater 3,700 kilometers from Perseverance, detected anomalous readings from its sample analysis at Mars Instrument. The chemistry of the settling dust wasn't just exotic, it was reactive. When mixed with Martian regolith and exposed to ultraviolet radiation, the interstellar organic compounds were forming new structures. Dr. Amara Okafor, a biochemist at NASA's Astrobiology Institute, was the first to recognize the pattern in the garbled data. "It's self-organizing," she breathed, staring at her screen at 3 a.m. "The carbon chains are forming vesicle-like structures. They're not alive, but they're protobiological. We're watching chemistry that might be the precursor to life, but from a completely different origin. The revelation sent shockwaves through the scientific community. For decades, scientists had searched Mars for signs of ancient life, traces of biology that might have existed billions of years ago. Instead, they were now watching potential precursors to life from another star system settling across an entire planet in real time. The contamination that planetary protection officers had feared as a disaster had become the most significant scientific discovery in human history. Mars wasn't just a testing ground for planetary defense. It had become a laboratory for studying the chemical building blocks of life from beyond our solar system. On November 9, 2025, Mars finally emerged from behind the sun. The first high-resolution images from Earth-based telescopes revealed a planet transformed. The polar ice caps were shrouded in a dark haze. The equatorial regions showed temperature drops of up to 18 degrees Celsius. The atmosphere, analyzed through spectroscopy, had gained measurable amounts of exotic carbon compounds detectable from 250 million kilometers away. Every spacecraft survived. Mars Express, feared dead, had simply been in safe mode, waiting patiently for the storm to pass. The orbital boost maneuvers had cost a fleet an average of 2 years of operational lifetime, but Harrison's gamble had paid off. Not a single mission was lost. But Mars itself had changed. The planet now wore a thin veil of interstellar dust, settling slowly toward the surface, carrying with it chemistry that would take decades to fully understand. Every rock sample, every atmospheric measurement, every future landing site was now contaminated or enriched, depending on your perspective, with matter from another star. 3 weeks after closest approach, astronomer Dr. Yuki Tanaka at the Subaru telescope in Hawaii detected something that made her hand shake as she reached her phone. 5 of the smaller fragments from 3I/Atlas's breakup had been gravitationally perturbed by Mars into new orbits that would intersect Earth's path in approximately 4 to 6 years. The fragments were small, none larger than 50 meters across, and the probability of impact was minimal, less than 0.3% for any individual piece. But they were coming. Humanity's first confirmed interstellar objects on a potential collision course with Earth, carrying with them the same exotic chemistry that was now transforming Mars. At the International Astronomical Union's emergency session, Dr. Tanaka presented her findings to a room full of pale faces. "We have time," she said carefully. "These objects are trackable. We can refine their orbits, calculate precise impact probabilities. If necessary, we can even attempt deflection. But," she paused, letting the word hang in the air, "this changes everything. 3I/Atlas wasn't a one-time visitor. It was a warning shot. The galaxy is full of objects like this, and now we know they can fragment, they can be perturbed, and they can threaten multiple worlds in a single pass." In the months that followed, space agencies worldwide quietly revolutionized their approach to planetary defense. The Mars orbiter fleet became a permanent early warning system. Their missions extended indefinitely. Construction began on a network of dedicated interstellar object tracking stations positioned around the solar system. Protocols were developed for rapid response missions to intercept or deflect threats before they reached the inner planets. The contamination of Mars, officially termed the Atlas event in scientific literature, became the focus of intense study. Rovers across the planet began systematic surveys of the settled dust, analyzing its chemistry, tracking its dispersion, documenting its interaction with the native Martian environment. Initial reports suggested the exotic organic compounds were stable in Mars' harsh conditions, potentially surviving for millennia. For astrobiologists, it raised profound questions. If Mars could be contaminated by one interstellar visitor, how many times had Earth been seeded with similar chemistry over its 4.5 billion year history? Were the building blocks of terrestrial life truly terrestrial, or had they arrived on countless comets from countless stars over the eons? On January 15th, 2026, Perseverance transmitted an image that appeared on the front page of every newspaper and news site on Earth. A close-up of Martian soil, dusted with the dark grains of interstellar matter, with the rover's robotic arm extending into frame. The caption, written by the rover's social media team, was simple but profound. "Visitor from the stars, now part of Mars, now part of us." As 2026 progressed, the fragments of 3I/Atlas continued their silent journey through the inner solar system. 5 were confirmed on potentially hazardous orbits. Dozens more had been lost in the sun's glare, their trajectories unknown. Every major observatory on Earth and in space maintained a constant vigil, updating orbital calculations daily, running impact scenarios weekly. In conference rooms and university laboratories, on late-night radio shows, and in congressional hearings, the same questions echoed. Were we ready? Could we deflect an interstellar object if we had to? What happens when the next one comes? And there would be a next one, with less warning and worse luck. The Mars fleet continued its watch, artificial eyes staring into the darkness, waiting for the next visitor from the stars. The planet below them slowly recovered from its artificial winter, temperatures climbing back toward normal as the dust settled. But Mars would never be quite the same. In its soil, in its atmosphere, in the data archives of every rover and orbiter, the ghost of 3I/Atlas would linger. On October 3rd, 2027, exactly 2 years after the closest approach, mission controllers at JPL held a quiet commemoration. No press releases, no public ceremony, just a team that had lived through those harrowing hours, watching silent video feeds of Mars at night, its auroras dancing, its sky transformed. "We were lucky," Sarachin said softly, nursing a drink as the Martian sunset played on the wall screens. "Next time, we might not be." "Next time," Director Harrison replied, "we'll be ready because of this, because we learned." But in the back of everyone's mind was the unspoken truth. In the vast, cold darkness between the stars, there were millions of objects like 3I/Atlas, some larger, some faster, some on trajectories that would give no warning at all. Humanity had survived its first interstellar close call. The question wasn't if there would be another. The question was when, and whether, when that day came, humanity would prove to be more than just lucky witnesses to cosmic disaster, but active defenders of a fragile, precious, irreplaceable home.